Joining us now to talk about topology and chirality, we have the winner of the von Hippel Award, Claudia Felser, from the Max Planck Institute for Chemical Physics of Solids. Thank you so much for joining us.
Yeah, thank you. I'm very proud to get this really prestigious prize.
Yeah. So in terms of chiral phenomena, I'm somewhat familiar with how life on Earth uses left-handed amino acids as opposed to right-handed, and it's somewhat of a mystery why that is. So how does thinking of chirality as a quantum number, how does that help with approaching mysteries like the homochirality of life?
Yeah, so this is a very good question, and it's also an unsolved question. So we know that if we want to make homochiral molecules, only one hand in this, we still have to use chiral catalysts. So we have to put structure chirality in to get structure chirality out. So it's a question of the hen and the egg. When has it started? To start from achirality, get chirality. So out. So far, even Ben List and Macmillan, they got the Nobel Prize to putting structure chirality and getting chirality out. So nowadays, there are some ideas about that the spin might have helped to get chirality. So if you have a magnetic material, so it favors the absorption maybe of one chirality. Okay. And some people think that this chiral light could be the origin. So in general, one could generalize this question by saying, can chiral fields help to get homochirality out of achirality? So this is a big question, and I think topology can help a lot because chiral electrons are playing a big role in topology.
Okay, yeah, that leads into my next question, which was how does this all connect with topological materials like vial semimetals?
Yeah, so in general, in topological materials, the electron, which has a spin, so the concept is that the electron and the spins are locked. And in this moment, the electron is also chiral. So, and we already know that, for example, chirality in wide semimetal can help to understand the asymmetry between matter and antimatter, a similar phenomenon like asymmetry between left-handed and right-handed molecules. So there we can make experiments in condensed matter which simulates the problems we have if we ask the question of the origin of the universe. Why do we have matter and not as much antimatter here? Right. So, and now is the idea, can we use this violation of chirality, which we know in the chiral anomaly, maybe to help us to also understand maybe the origin of life.
Oh, that would be exciting.
This is exciting, but unsolved.
Right. So you won the von Hippel Award for predicting and experimenting with new topological quantum materials. What sort of applications do you think that these materials could have?
So there's one fancy application. So you could have topological protected quantum computing. So you can make quantum computing and you don't have the problems of noise and so on what you would have with superconducting quantum computers. But this is also not solved yet. But what we like to do, what we are doing and even seeing very nice effects already is that we can enhance maybe thermoelectric effects. So we see much higher efficiencies based on the topological properties. So we get an extra contribution in the conversion of heat into electricity based on topology. But the most exciting question then goes back to the origin of life is catalysis. So we see that with the topological materials, even applying external forces like a magnetic field, we can enable catalytic reaction which we otherwise would not observe. And this is what really excites me mostly.
Yeah, it definitely sounds like some exciting stuff. Thank you so much for joining us here today, and I hope you have a great rest of your week here at MRS.
Yeah, thank you very much for inviting me.